We start this lecture with an overview, a plan for what will be presented. This pre-lecture expands our study of mechanics from single particles to systems of particles. We will introduce the very important concept of the center of mass of a system of particles and determine the center of mass for both discrete and continuous mass distributions. We will use Newton's second law to obtain the equations of motion for the center of mass of a system of particles. We will also obtain a version of the work kinetic energy theorem called the center of mass equation that can be applied to a system of particles. So far, we have only considered the motion of simple objects. We have intentionally not considered the motion of, for example, an object composed of two different sized balls connected to the ends of a rod. In the next few pre-lectures, we will develop the tools to understand the motion of more complicated systems of objects such as these. We will discover that their behavior can be understood by applying what we already know, and we will see that the equations describing their motion are remarkably similar to those we have already developed. We will start by introducing a new concept which will play a key role in what follows, that of the center of mass. Quite simply put, the center of mass of an object is just the average location of the mass that makes up the object. For a simple symmetric object like a ball or box of uniform density, we will see that the center of mass is just at the center of the object. For less simple shapes, we will have to perform a calculation to determine the location of the center of mass. The procedure we will adopt for finding the average position of all of the mass contained in some system of objects will be to simply take a weighted average of the positions of the individual parts. Namely, we will define the location of the center of mass of a system of particles to be equal to the sum of the positions of the individual particles, with each one weighted by its own fraction of the total mass of the system. On the next slide, we will determine the center of mass for a two-particle system. This concrete example will illustrate the general procedure and hopefully make clear why this definition makes sense. We'll start by considering a system of only 2-point particles, labeled 1 and 2. We will assume that we know the masses of the two particles as well as their locations along the x-axis. Since the particles lie along the x-axis, the calculation of the position of their center of mass is straightforward. If the masses are equal, we see that the center of mass is located at the average value of x1 and x2. This position is halfway between them, which certainly makes sense. If, on the other hand, one mass is twice as big as the other, it will count for twice as much in the average, which means the center of mass will be closer to the heavier particle than the lighter one, which also seems reasonable. This procedure for defining the center of mass can easily be extended to more than one dimension using vector addition. Here we illustrate the general expression for the displacement vector for the center of mass and show how it can be written in terms of the difference in the displacement vectors of the two particles. The beauty of this approach is that we can see that the location of the center of mass does not depend on our choice of the origin or the orientation of our coordinate system. The center of mass always lies at the same fixed point along the line connecting the two objects. We have just demonstrated an important result, namely that the center of mass is a property of the system itself. It does not depend on the way we choose to look at the system. Indeed, in a few pre-lectures, we will show that the center of mass of a rigid system is the same as its balance point. We can extend our definition of the center of mass for systems containing more than two particles by simply summing up the mass-weighted displacement vectors for each particle. It is usually easier to break this vector equation into components and evaluate each component separately. Just to make sure we know how this works, let's do an example involving 8 equal mass particles located on the corners of a cube, as shown. To find the x-coordinate of the center of mass, we need to sum the x-coordinates of each of the 8 particles weighted by the ratio of the mass of each particle to the total mass of the system. In this example, the particles all have the same mass, and their x-coordinates are either 0 or L, so that the sum is easy to evaluate. and we find that the x-coordinate of the center of mass is just equal to 1/2 L. We will get the same results for both the y and z coordinates, so that we see that the center of mass is at the center of the box as expected. Now, suppose the cube was a solid made up of millions of atoms, rather than just 8 particles on the corners. We suspect the answer would be the same, that the center of mass is still in the middle. But how can we prove this conjecture when actually performing the sum over millions of atoms seems difficult, if not impossible? Well, once again, calculus comes to the rescue. Rather than calculating the product of position times mass for individual particles, we just integrate the position vector over all infinitesimal mass elements, dm, contained in the cube. This procedure may sound difficult, but it's really not that bad, and we will walk you through the details of this calculation on the next slide. Before we actually evaluate any integral, let's make sure we understand exactly how we adjust our definition of the center of mass when we are dealing with a continuous mass distribution. The big idea is that we have to replace a discrete sum by a continuous sum, an integral. In the discrete sum, we evaluated the product of the mass of each part of the system and its position and then added them up. In the continuous sum, we are doing the same thing. The only difference now is that we are dividing a continuous object up into an infinite number of tiny volume elements, each having a mass dm. Since we are integrating over the volume of a cube, a three-dimensional object, the integral itself must be evaluated in all 3 dimensions, x, y, and z. The volume of a tiny volume element in this coordinate system is given by dx, dy, dz, and the mass of this element is the product of this volume and the mass density of the material making up the cube. Call it rho. Our job now is to evaluate this triple integral. The first step is to break our equation for the center of mass vector, RCM, into x, y, and z components. We'll start with the x equation and first determine the limits of integration. In each direction, the cube is located between the origin and a distance L from the origin. If we assume the mass density rho is a constant, then it can be taken outside of the integral. The resulting three-dimensional integral factors into the product of 3 separate integrals, one for each direction. Evaluating the y and z integrals, we find that they are each just equal to L. Evaluating the x integral, we find it is equal to 1/2 L squared. Putting this all together and rewriting the product of the mass density and the volume of the box as the total mass of the cube, we get the expected result, that the x-coordinate of the center of mass of the cube is just equal to L over 2. The y and z component calculations are absolutely identical to the x component calculation, giving us the expected result, that the center of mass of the box is at its center. We now know how to find the center of mass of a collection of point particles as well as that of a continuous solid object. What happens when we want to find the center of mass of a collection of solid objects? Here we see 2 objects labeled A and B. By definition, the center of mass of the system is found by integrating the position vector over all of the mass in the system. Since the system is made of 2 objects, the total integral is just the sum of 2 separate integrals, one for each object. If we multiply and divide each of these integrals by the mass of the object, we certainly haven't changed anything, but we can now see that the numerator just becomes the mass of each object times the position of its center of mass. Therefore, we have just arrived at a simple procedure for finding the center of mass of a system of solid objects. Namely, we just treat each object as a point particle with all of its mass located at its center of mass. That's all there is to it. So far today, we have defined the concept of the center of mass and have shown how to find it for any system of objects. With this knowledge in hand, we can finally do some physics. We will start with our definition for the center of mass of a system of objects and take the derivative of this expression with respect to time. The left-hand side of the equation becomes the velocity of the center of mass, and the numerator on the right-hand side becomes the sum of the mass times velocity for each object in the system. We will now take another derivative with respect to time. The left-hand side of the equation becomes the acceleration of the center of mass, and the numerator on the right-hand side becomes the sum of the mass times acceleration for each object in the system. The product of the mass and acceleration of an object is just equal to the total force on that object. Now, this sum of the total forces acting on all objects in the system could get unwieldy if the number of objects gets large. The really good news, though, is that we can simplify this sum immensely by realizing that any forces that act between two objects that are both in the system will cancel in this sum, since we know they always come in pairs of equal magnitude and opposite directions. That's just Newton's third law. Hence, the sum of all forces acting on all objects in the system just reduces to the sum of all forces acting on the system from the outside, or the total external force. We have finally arrived at something that looks exactly like Newton's second law. But rather than applying just to point particles as before, this expression relates the total external force on the whole system to the acceleration of the center of mass of the system. Consequently, we can say that no matter how complicated a system of objects may be, the center of mass of the system behaves in the same simple way that a point particle does. Indeed, on the next slide, we will use this equation to obtain a generalization of the work kinetic energy theorem for systems of particles. In Prelecture 7, we integrated Newton's second law to obtain the work kinetic energy theorem for point particles, namely that the change in kinetic energy of a particle is equal to the work done on that particle by the net force. We will now extend this result to systems of particles. We start from our result from the last slide, that the acceleration of the center of mass of a system of particles is equal to the total external force acting on a system of particles divided by the total mass of the system. This equation looks exactly like Newton's second law for a point particle that has the total mass of the system, m, and is located at the center of mass of the system. Consequently, we can perform exactly the same derivation we made in Prelecture 7 to obtain the work kinetic energy theorem for a point particle. Now, the result here will be an equation, often called the center of mass equation, that looks exactly like the work kinetic energy theorem we derive for point particles. The only differences lie in the subscripts. Now, these subscripts are important, however. The change in kinetic energy term is calculated as if the system were a particle of mass m and were moving with the velocity of the center of mass. We define the right-hand side of the equation as the macroscopic work done by the net force. This macroscopic work is calculated as if all forces were acting on this particle located at the center of mass. We can now see why we did not need to worry about the microscopic work done by the kinetic friction when we were calculating the motion of the box skidding to a stop in the last pre-lecture. If we consider the box to be a system of particles, we see that the change in kinetic energy of the box is exactly equal to the macroscopic work done by the net force, the kinetic friction force. The microscopic work done by the kinetic friction force at the interface of the surfaces of the box and the floor determines the additional thermal energy in the box and the floor, but does not determine the motion of the center of mass of the box. We will end with a simple example to illustrate some of the concepts we have developed in this pre-lecture. Imagine you are an astronaut far out in space. You have just finished fixing a space telescope using a big wrench whose mass is 1/10 as big as yours. You realize you have no way to get back to your spaceship, which is 20 meters from you. So you throw the wrench as hard as you can in a direction away from the spaceship, which causes you to move in the opposite direction, toward the spaceship. When you finally reach the spaceship, how far away from you is the wrench? The key concept in solving this problem is that the acceleration of the center of mass of a system will be zero if the external force on the system is zero. In this case, we'll define the system to be you and the wrench, and the center of mass of that system is initially at rest, a distance of 20 meters from your spaceship. Since there are no external forces acting on the system, and the center of mass is initially at rest, the location of the center of mass of the system can never move. If we choose the initial location of the center of mass to be at x equals 0, the center of mass will always be at x equals 0. The location of the center of mass of the system is determined by its definition, namely, your position times your mass plus the position of the wrench times its mass divided by the total mass of the system. Multiplying both sides by the total mass doesn't change the fact that the right-hand side is 0. So with some algebra, we find a simple equation for the location of the wrench in terms of your location. The wrench is always going to be 10 times as far away from the center of mass as you are, and it is always on the opposite side of the center of mass from you. When you are at the spaceship 20 meters to the left of the center of mass, the wrench will be 200 meters to the right of the center of the mass, which is 220 meters from the spaceship. We conclude with a brief discussion of the main points of this prelecture. First, we define the center of mass of a system of particles as the mass-weighted average of the locations of the particles. We generalize this definition to continuous mass distributions by integrating over the distribution. Second, we applied Newton's second law to a system of particles to obtain the equations of motion for the center of mass of the system. In particular, we found that the acceleration of the center of mass is equal to the total external force acting on the system divided by the total mass of the system. Third, we integrated the equation of motion for the center of mass to obtain the center of mass equation that relates the change in the kinetic energy of the center of mass, calculated as if the system were a particle having the total mass of the system and moving with the velocity of the center of mass, to the macroscopic work done by the total external force, calculated as if all forces were acting at the center of mass.